So let me step you through solving some of these problems. And your goal here should be to use the 5-step process that I've outlined. And if you're doing this properly, your work should look like mine. I'm looking for very specific things when I grade these things. I'm looking for all the elements of the 5-step process. And as I go through, I'll point them out to you. So here's, I've gone through part way on this process already for you on problem number 2. So we've got 2 trains here. This is an interesting problem. Typically, we only are dealing with one moving object. In this case, we're dealing with 2. So this is a little bit of an unusual problem, but it's an interesting problem, classic problem. And the first step of the 5-step process is to draw a diagram. And you'll notice on the diagram, I have an x-axis and I've labeled it. And what I've done is I've drawn my 2 objects in here, and I've got object train A, and I've got train B at their initial points. And train A starts out in Boston, train B starts in Chicago. And at time 0, this one's at 0 miles is its initial position. And this one starts out over at 1,600 miles. And what I've done is down below, I've made a table of initial conditions. This is actually part of step 2 of the 5-step process, is to label your diagram with your data, which I'm doing up here with the little boxes with the numbers. And I'm also just making a quick summary of the initial conditions. So I'll need those to plug into my equations later. So, for the Boston-bound train, we start out at 0 miles, which I've written down here. We have a constant velocity of 80 miles per hour. So our acceleration for these problems is 0. So technically, this is a case of constant acceleration. And I will use constant accelerations for this. But it turns out what you can use rather than the constant acceleration problems is just the speed equals distance over time formula. Or same thing you could write as distance equals speed times time. And you're going to see when I work this out that that's exactly what happens. So we've listed out what the initial condition for each object is, and we've drawn them up here, both here and here. And now let's go through and see what we need to find. What they asked us to find is where the 2 trains meet. All right? So that's what we have to do, both the where and the when. And so we're going to have to look back at that in a second. Step 4 of the 5-step process is to identify what equations apply to the situation. And in this case, I typically tell you, as novices at least, start out with equation 5. Actually, equations 5 and 6. In this case, equation 6 isn't going to be that useful because this is constant velocity. So the equation 6 will just turn into a constant function. Not very useful. But equation 5, I'm going to go ahead and show you how we can use this. And I'll show you how it turns out to be the same thing as our distance equals speed times time formula. So we actually have 2 objects. We've got object A and we've got object B, a train from Boston and a train from Chicago. So I'm going to have to write a motion equation for each one of these. And so I just wrote down our general equation for each, but you'll notice I'm using a subscript A for the Boston train and B for the Chicago train. And the question is, what are we going to plug in for each one of these equations? Well, our acceleration of each of these is 0, so we can knock out the acceleration. Our initial position for the Boston-bound train, for the train leaving Boston, is 0. For the Chicago train, it's 1,600 miles. And remember, typically on these types of problems, I don't like to use, in general, miles or kilometers. I generally convert to meters or feet. But because we're using miles per hour, the track lengths are in miles, and we're using time in hours, it looks like those units are going to work for us. I'll just stick with miles and hours for our units. Our velocity for the Boston train is 80 miles per hour. The velocity for the Chicago train, and it looks like I left the T out of my equation here, is 100 miles per hour. But you've got to be careful. These are vectors. And you'll notice here, I've got a question mark. Our Boston-bound train is positive 80 miles per hour. Our Chicago train moves to the left, and that's going to be negative 100 miles per hour. So we need to make sure we have a negative sign in here. So, and then the other thing that I made a note of down here our time for the Boston train, it says it starts out at noon, and I defined up top here that my initial time is noon, and I called that 0. That's my time 0. And in my problem, it says at noon in Chicago, their train departs with a speed of 100 miles per hour. Well, noon time in Chicago is different than noon time in Boston because you have a time zone difference. And so noon in Chicago happens 1 hour after noon does in Boston. So the Chicago train leaves an hour after the Boston train is. That's a little nuance here you got to be careful of. Now, would they give you something like that on an AP exam, or would I give you something like that on a quiz? Now, that's really a little twist or a little trick, and I wouldn't be that mean, unless I have a really bad day, of course. And then I might give you anything in that case. But generally speaking, this you would see in book problems, and you will see in web assignments problems that are similar like this, which have some of these twists, which are good to think about and know how to model these, because they happen in real life. So the question is, how do we handle that difference in time? Well, if you look at your equation, if I were to plug in my initial time into the Boston train as zeros, I should end up with my equation. Let me just write down my equation with my numbers plugged in. So I'm going to zero out my acceleration. So I have my position for the Boston train is 0 plus 80 times time plus my initial position, which is 0. So that's my equation for the Boston train leaving Boston going to Chicago. And if I plug in a time equals 0 in this, I should get a initial position of 0, and it does. If I plug a 0 in for time, I'll get a 0 for my position to start. If we do the same thing for the Chicago train, watch what happens. I've got my Chicago train leaving for Boston. My acceleration is 0, so that's gone. I've got negative 100 t. Plus, don't forget, I'm actually starting out in Chicago, which is at the 1,600 mile mark on my number line here. So if I were to use the same time frame for the Chicago, if I were to put a time 0 in here, at time 0 in Boston, the Chicago train hasn't left yet, and so it shouldn't be moving yet. It should actually, at time 1, when I plug a time 1 in here, that's when we should get our 1,600 miles, because it hasn't moved anything yet. At time 2, we should have moved for 1 hour, and we should have subtracted 100 miles off of that, and so on and so forth. So the problem is, I need a 1 to be more like the 0 in our previous equation on the left side here. So what do I do for my time in this equation so that when I plug a 1 in, it acts like a 0? Well, what we can do is this. Our train B is negative 100, and what we'll do is we'll just do t minus 1, the time shift. And you've done these in math before. You've seen left and right shifts along your axes. Along your x-axis, you do an x minus 1, shifts your function to the right one. We're doing the same thing here. So when I plug in time equals 1 hour in here, it acts as if it's like the 0 time for the Chicago train. That's our starting time for the Chicago train. Now, going back to our equations, so these are our two equations that we can use to solve the problem. So step 5 is to solve. And what do we know? That's what we're going to look down here, what we've identified. Well, the key is we need to figure out where the trains meet. When the trains meet, that's when XA, its X position for the A train equals the X position for the B train. So we're going to set these two equations equal to each other. So I've got 80t equals negative 100 t minus 1. There's my time shifts for the extra hours waiting before it starts, plus 1,600. Now what you're going to do with this equation, solve this equation for time, and that'll give you the time that the trains meet. And once I figure out that time, I can then go ahead and substitute into either of these two equations. In fact, I would maybe substitute in both to make sure your answers work. Actually, I'm sorry, I mean into these two equations. Sub that time in, you will find the positions. And the positions for the A train and the B train should match. And that's how you solve that problem. All right, so now let's suppose we have a basketball dropping here. So we've got by the way, it's a $150 basketball because that's how much your basketball camp costs. But she gets a free basketball at the end. And we have 3 or 4 of those collected now. She goes to camp every summer. That's my daughter, Sophia. Suppose you drop a ball from a height of 2 meters, state any assumptions, and then find the time it takes to reach the ground, the velocity of the ball as it reaches the ground, and the average velocity of the ball over the entire fall. Well, you've seen this before. We did this as an experiment earlier on, and I actually had you dropping objects and just taking some measurements and calculating average velocities and trying to figure out what the acceleration was. Well, now we have more theoretical knowledge and equations to use to actually predict what that is, and you can check your answers against those. So I've started the problem here already, and you can see step 1 in the process is to draw a diagram. I've drawn a y-axis, and I've also drawn a bit of an x-axis down at the bottom here, and I'm using this blue line for the x-axis to represent my ground level. All right, and my y is in meters, and my x would also be in meters, but we're not moving left and right, we're only moving up and down. And then what I did is I've drawn in here, here's my starting position for the ball, and that's up at 2 meters. And the question is, what's my starting velocity? Well, we're starting from a stop with the ball, we're letting it go. So this is going to be 0 meters per second. All right, and I've drawn in my table of initial conditions. This is really getting to part 2 of the 5-step process to list your data. And we've drawn our initial point where the ball is over here, and I'm going to list the data for it. It starts out at positive 2 meters. And it's really important that you start thinking about positive and negative on these numbers, because these are vectors and they have both a direction and a magnitude. So the plus and minus sign gives you the directional piece. We're starting at 0 meters per second for the ball, starting from a standstill. And the question is, what are we going to use for acceleration? Well, here's where our assumption comes in. We're going to assume free fall. And free fall, of course, means that the only force acting on the object is gravity. And the force of gravity on Earth is a constant, and we've demonstrated why that is in class, or we've talked about it a little bit at least, and you should take a scale and see for yourself if it works. Still waiting for somebody to go up to the top of a mountain and measure their weight. So free fall means that the only force acting on it is gravity. Gravity is a constant force on Earth, and if it's a constant force, forces cause acceleration, so the acceleration should be constant as well. So that's a constant acceleration assumption. And so therefore, our acceleration in the y direction should equal minus the gravitational acceleration constant, which is negative 9.80 meters per second squared. Now, generally speaking, on a simple problem, we would use 10 meters per second squared, but because this relates to some lab data you do, I'm going to go ahead and use the negative 9.80 meters per second squared to solve this problem a little more accurately. All right, so that's step 1 of step 2. Step 3 is to figure out what you need to find. And what we need to find is actually listed in our problem up here. So this is step 3 is sort of laid out for us. So we're going to find the time to reach the ground and the velocity to reach the ground. And what you want to do is you want to draw that on your diagram. And you can see down here, I've drawn what I call a point of interest, some later point in time or space that I'm interested in finding things out about. And then I just list some things I know about it. So at the ground, what do I know? Well, you know something. You always know a position, a velocity, or a time. In this case, I know what the position is. The position at the ground is 0 meters. Don't make the mistake of saying at the ground you're not moving anymore, so you have 0 velocity, because that is false. We're talking about free fall here, and the only force acting on this ball is gravity, and so nothing else can be affecting the ball, including you sitting on the earth and the earth pushing on you. So this only works when you're in the air. So we're actually looking at the time frame just before it hits the ground, the moment in time just before it hits the ground. Our height is 0, and we would like to find our final velocity, v1, vy1, and the time it takes to get to the ground. Those are the 2 things we'd like to find. So that was step 3, sort of to identify those items. Step 4 is to write down equations that apply. So what relationships apply to the situation? Well, we've got constant acceleration equations we get to use with our assumption up here for acceleration. So, and my argument is we can always use steps 5 and 6, equations 5 and 6. And remember, those are my numbered equations, generally speaking. Other books or whatever would have other ways to number those. So I wrote those equations down, and what I want you to do is the first thing after you write them down, go ahead and plug in for your coefficients right off of your table of initial conditions. And so our acceleration is going to be negative 9.8. We're going to plug in 0 for our initial velocity and positive 2 for our initial height. And when we do that, simplify a little bit, so we're going to get negative 4.90, if you want to be, we have 2 significant digits here actually, 3 significant digits, t squared plus 2. All right, so there's our position versus time equation. Do the same thing for the velocity versus time. We can plug in negative 9.80 times t plus our initial velocity is 0. I circle those 2 equations because those 2 equations are extremely important. Those tell us the position and velocity at any point in time that we would like in the future. Or if we pick so we could actually plug in a time and get a position and velocity. Alternatively, we could plug in a position, or we could plug in a velocity, and we could solve for the time either of those things happen. So you can use those both ways. So our next step is to solve for our time and velocity. So I'm just going to refresh my memory. At the ground, what do I know? I know that my height is 0. My y value is going to be 0 meters. Well, guess what? That can only fit one place. It's going to plug in right there. And so I'm going to go ahead and plug that in. 0 equals negative 4.90 t squared plus 2. And now all you have to do is go ahead and solve this for time. And I'm going to leave that math to you. And you'll find, actually, you're going to get 2 values for time because this is a squared equation. And you should actually reject one of those 2 values. And we should talk about it in class a little bit. Ask that question. How do I know which one of these to reject, and why do I get the types of numbers I get? Once I find that time, so I'll get whatever time I have, I can take that time and I can plug it over into this equation, and I can find my final velocity. So I'll leave the rest of that problem to you to work. Now, what happens in problem number 4? Now you're dropping the ball from 5 meters. So this is a very similar problem, obviously. So should you step through this problem and do every single bit of work all over again? And the absolute answer is absolutely not. All you're going to do is you can take the equations from last time. What were our equations that we had last time? We had y equals negative 4.90 t squared plus 2, and we had our vy equals negative 9.80 times t. All right, so this was equation 5, our motion equations for constant acceleration, and equation 6. Now, the only thing we need to do to change this situation is move our height up with that ball. So just change this equation 3 to 5, and then redo your calculations, and then that will give you your answer to that problem. So whenever you can reuse work from a previous problem, go ahead and reuse that work. That's perfectly fine to do. Just make a quick comment. I'm reusing the equations from problem number 3 or whatever, and then write down the equations, modify them as necessary, and finish up the problem. Don't start from scratch when you don't have to. All right, so now we're going to talk about a Tesla Model S, that's their sport version, P90D, about $120,000 car. So this car goes from 0 to 60 in 2.5 seconds. These were the numbers from 2016. In 2017, it actually is going faster than that. So it's a pretty quick car. We'll use these numbers, though, to solve the problem. And so they asked us to find a few things. I've started up the problem again for you here. And once again, step 1 of the 5-step process is to draw my graph. And you'll notice that I'm drawing an x-axis again. Please make sure that when you draw your diagrams, they're not the size of a quarter. They should be 6 inches long. So you've got a 6-inch x-axis or a 6-inch y-axis. If the object's moving left and right, use an x-axis. If it's moving up and down, use a y-axis. I've drawn in the initial position of the car and the final position of the car. And I've sort of labeled in a nice order here, which gives me my initial conditions table. My initial position is 0. Don't ask me why I put miles per hour there. Let me correct that. Is 0 miles. Or actually, we're going to use, what unit should we use here? I'm going to use feet on this because I like using room size units generally speaking. So I'm going to use feet for this. Our initial velocity is 0 feet per second. And the question is, what are we going to use for acceleration? And is this a constant acceleration situation? Let me come back to that. Later on, we're at some position, which we don't know, but they did tell us that our final velocity is 60 miles per hour. And the asterisk up here, when it says 0 to 60, we're talking in miles per hour. And so we know at the end of our situation we're interested in, and we're at 60 miles per hour, which is 88 feet per second. And remember, that's something you should have memorized, so you don't have to go through that conversion process. We were also given that our final time was 2.5 seconds. And so we know a couple of things. We know two things at the ending point. Now, at this point, I would normally look at and plug in an acceleration number, but I don't know an acceleration number. But they did give us a change of velocity, and they gave us a change of time. So we can actually calculate average acceleration, which actually they asked us to do in Part A. And when I found that, it was 35.2 feet per second squared, or 24 miles per hour per second. They also asked us to figure out how many G's that was. And remember, G's is just comparing your acceleration to the acceleration of something dropping on Earth, which is 32 feet per second squared. You can take the ratio of those two numbers. Always put the Earth's number on the bottom. That's your reference number. And it turns out that's 1.1 G's. All right, and we'll be talking more about G's later. But it's just a ratio of your acceleration to the Earth's acceleration. And now, what about my assumption here? Is this a constant acceleration at 35.2 feet per second squared? Or is it non-uniform? If it's non-uniform, technically I can't use my constant acceleration equations. And we've seen on the Corvette problem that we did, it's certainly not a constant acceleration when that Corvette was going from 0 to 200 miles per hour. However, this is a much shorter speed to attain. And if you look back to the Corvette lab, you would actually see that it's fairly constant and fairly linear, go from 0 to 60 on the Corvette. And it's probably, pretty likely that it's somewhat similar situation here, where it's fairly constant change to get from 0 to 60 on the Tesla. And Teslas, by the way, don't use a transmission like that Corvette did, so you don't have the shifting issue either. And so I'm going to make the assumption that it's fairly uniform acceleration, and I can write a sentence or two explaining why I think that is, and to justify that. And I'll go ahead and use my 35.2 feet per second squared and assume that's constant acceleration. And once I do that, what do we have to find? Well, they actually asked us to find what the distance traveled is over that time frame. So I'm going to write down my equations 5 and 6. And of course, if I'm finding distance traveled, I really only need equation number 5. And when I plug in my numbers, I'm plugging in my 35.2, a 0 for initial velocity, and 0 for the initial position. And I get a very simple equation. My position equals 17.6 t squared. And all I need to do now is plug in my time. They gave us a time. So go ahead and plug in 2.5 seconds into this equation, work out your numbers, and you will get the distance traveled. I did that over here. And I plugged in my number here and calculated, and there's my answer. And this is the type of work that you can show me. Just show me the plug-in, and then you can go ahead and calculate in your calculator, write down the final answer. Please remember to round carefully, and please remember to give me units. All right, so we answered part C. That's fine, and we talked about the assumptions. All right, we've seen our rocket bike video, and we know and love our rocket bike folks from France. Here's a startup to this problem. We've got, we start with drawing our x-axis as usual. That's our diagram. I've got our object. Our rocket bike starts at time 0, and here we are at some later point in time. Now, you remember from the video, they actually estimated that it reaches top speed at around 250 meters. And of course, we actually looked on the video, and we we figured out the time was around 5 seconds to do that. We did our calculations based on that. So we're going to do this a little bit different fashion here. So they ask us to find the average acceleration. Well, our average acceleration formula from before is going to be fall a little bit short for us here. But let's go ahead and take a look at what information we give and sort of organize our thoughts before we start. So we've drawn our diagram, just a simple x-axis. We're going to use meters for our units here and seconds for time. We start out at 0 meters. We have our initial velocity 0 meters per second. They told us that our final position, that we hit our 333 kilometers per hour is 250 meters. So we've got that to work with. And I took our 333 kilometers per hour and I converted it to meters per second. All right, so we have a final position and a final velocity. What we don't know is the time that happens, and we don't know what the acceleration is. Once again, this is sort of like the Tesla problem. I don't know for sure that this is a constant acceleration problem, but the rocket has fuel that it burns, and if we sort of make a general assumption that as it's burning its fuel, it has a constant pressure out of the nozzle to push that forward, we can assume that roughly speaking it's constant acceleration, or at least constant, close enough so that it'll give us a rough idea of what these numbers are. So even if we're not truly sure if it's constant acceleration or not, we can still use a constant acceleration equations to get us a rough idea what the numbers might be. So we're asked to find the acceleration and this final time, all right, I already have the blanks ready to go up here to fill in our answers. All right, so let's take a look at acceleration. All right, so the problem I mentioned before is that if we use equation number 4, that can be used any time we want. This is not a constant acceleration equation. This is how we find the average acceleration. All I need to know is find a change of velocity over change of time. Well, it turns out I know my change of velocity. My change of velocity is positive 92.5 meters per second. So I know that. What I don't know is my change in time. So it's sort of hard to use that equation. So what I've done is I've written down, once again, assuming we're going to use constant acceleration to run this vehicle, I'm going to write down equations 5 and 6, my go-to equations, and see what happens when I use those. And the first thing I'm doing right over the top of this, I'm just checking off to see what I know. This is another technique to use to see which equations will help you or not. For example, this x represents our final position or later position of the ball at our point of interest. We know that. Our acceleration, we don't know. That's an unknown, so I put a question mark over the top of that. We don't know the time it takes. That's another question mark. Our initial velocity, we know, is 0. We know that information. We don't know this time it takes to get to our 250 meter position. I do know my initial position is 0. All right, and when I plug in the things I know, this is the equation I get. The problem is, if I were to plug in my 250 meters on the left side of the equation, because we know that's our final position, I still have 2 unknowns here, and that's a little bit of a problem. Well, let's see if equation 6 will help us better. So we actually know our final velocity. Our final velocity is what? 92.5 meters per second. Our acceleration we don't know. That's the unknown we're struggling to find. Our time we don't know. Our initial velocity is a 0. So when we plug those in, we have this equation. And remember, we do know this one value here, which is 92.5 meters per second. All right. But once again, I have 2 unknowns here. Well, I've got 2 unknowns here. And I've got 2 unknowns for equation 5. Lucky for us, those are the two same unknowns. And this is a system of equations. I've got 2 equations with the same 2 unknowns, so I can use a system of equations. So let's go ahead and plug in our numbers and see what happens here. So let's see. You know what? I'm going to do this without plugging in. No, I'll go ahead and plug in numbers. I like to do things with general solutions, and you'll see later what I mean. But for now, let's go ahead and plug in some numbers, try this out. So I've got 250 equals 1/2 AX T squared. My second equation is I have 92.5 equals AX times T. All right. Now our goal here, I've got my two unknowns, AX and T, and I've got two equations. And so what I can do is I can solve, I can do this a tricky way too. I can actually solve in this equation for one of these two variables and substitute out to eliminate one of the others. And I think what I'll do here is I will solve for, in this equation, I'll solve for AX and then substitute it out in this equation. So I've got AX equals what? I'm going to divide both sides by T, and I get 92.5 over T. Now that value I can substitute in right there. So I'm going to do that. So I've got 250 equals 1/2 of, and I've got 92.5 over T times T squared. Nice thing is one of our T's cancels here. So I've got, and if I do a little bit of math here, I'll multiply both sides by 2. So I've got 500, and I'll divide by the 92.5 equals, there's my time. All right. So 500 divided by 92.5 is a little over 5 seconds, which is about what we predicted out of the video. Let me just calculate this. 500 divided by 92.5. So this is 5.4 seconds. And we had actually predicted it was around 5 seconds. And then, so that's the time it takes to reach 250 meters. But then they ask us, what else? How long did it take to move? And then the acceleration. Well, the acceleration, we can go back to, now let me switch colors here. We can go back to this equation and plug in our time right there. So we have AX equals 92.5. And remember, that 92.5 is actually meters per second if you want to see the units here. Divide that by our 5.4 seconds. That's meters per second per second. So I've got 92.5 divided by my 5 I'll use some of my digits here, 405, so I don't lose any of my accuracy. So I end up with my acceleration is 17.1 meters per second squared. Okay. So, all right, 17.1 meters per second squared. That's, by the way, that's about what we got when we looked at the video and used our timing. So there's our answer. They also asked us how many G's. So now we can go back and answer that question. The G's, I can just take the rocket bike's G's divided by the Earth's. And so I'm going to take, remember, it's just a ratio. And so the Earth's G acceleration is 9.80 meters per second squared. The rocket bike's at 17.11 meters per second squared. And if you divide those two, you get about 2. So that's about 1.75 G's. And what that means is when he's actually accelerating, he feels 1.75 times his own body weight. The question is in what direction? And this is sort of unusual because normally you feel your body weight acting downward. He would feel it acting from forward to backward. He's trying to pull him off that motorcycle, or that bicycle, should I say. It asks another question here. How fast could the bike go from 0 to 60? Well, actually, I think now we could maybe use this equation to answer that. Because now we know what the acceleration is. We know our change of velocities is 0 to 60 miles per hour. We want to convert to meters per second. And then we can just solve for time. So I could actually rewrite this equation. The time it takes to do that would be, I can just exchange my means and extremes here. It's your change of velocity divided by your acceleration. And so we would have, and check me if I'm wrong, remember this 60 is 60 miles per hour. When you hear 0 to 60, somebody saying that in America, that's what it means. And I think that's what that 27.8 meters per second divided by 17.11 meters per second squared. Look at our units, meters per second canceled, and one of our seconds is going to flip up top. And that's how long it'll take us. So 27.8 meters per second divided by 17.1 is about 1.63 seconds. Now remember, the Tesla, which is one of the fastest cars out there, did this in about 2.5. Now it does it at about 2.28 seconds, and this is quite a bit faster. So this would blow the doors off of a Tesla. All right, here's another quick car. This is a $1.8 million car. They only make 30 of these things. And this has the fastest quarter mile. And they call this a production car. They make 30 of them. They call it a production car. I don't think so. But and Tesla also makes it on that list too. And they're a true production vehicle. All right, so what do we do to solve this problem? I've already got a head start here. Once again, step one is just to draw a diagram. So here is my diagram. I'm going to use my x-axis. What units do I want to use? Well, we've got miles going on here, so I'm probably going to convert everything into feet. And so here's my initial starting position. I'm at 0 feet. My initial velocity for my table of initial conditions is 0 feet per second. And once again, we're in a situation, well, what do we do for acceleration? I'm going to make the same type of assumption that we did before. It's a simplifying assumption. It might not be exactly true, but it's probably pretty close to true, that this car is going to accelerate fairly uniformly as it goes for the quarter miles in 9.7 seconds. And for evidence for that, we can refer back to our Corvette data. We saw that within any one gear, it was a fairly uniform acceleration, and over 9.7 seconds is probably going to be pretty close. All right, so we can write out an assumption, explain it in 2 or 3 sentences, and explain why we're going to do that. Okay, so they ask us in part 3 of the 5-step process to find our acceleration. And we made an assumption already here that it's going to be constant acceleration. And they asked us to find the final velocity at this point. All right, so how do we find our acceleration? The number of G's based on the acceleration, and we can compare this to the rocket bike to see if this is faster than the rocket bike. And then how fast is this car moving after a quarter of a mile? Well, I've already written down the relationships we can use, which is part 4 of the 5-step process. Remember, equation 4 is just our average acceleration equation. We can use that whether we're constant acceleration or not. This is just an averaging function. And then I've written down a few of our favorite equations, equations 5, 6, and 8, from our constant acceleration equations. And let's just check off what we know and what we don't know. All right, so we know initial and final positions for this thing. So we'll know initial and final positions. We know our initial velocity is 0. We actually know our time is 9.7 seconds. So we know our time. So if you look at this equation, I've checked off everything except for one thing, which is the acceleration. So I can actually use this equation to figure out acceleration. So I'm going to go ahead and throw in our numbers here directly and see what we get out here. Well, just to be formal about this, typically what I ask you to do is just to plug in what you know in terms of your coefficients, which would be this number, and this number. So let's just do that first as a good first step, and then we'll go through the solution. So we don't know what the A is, so it's 1/2 AX t squared. We know our initial velocity is 0, and we know our initial position is 0. All right, so that's equation 5 for us. All right, done. So part 5 is to solve for AX, and we know what? Go back up to what we know that we written next to our point of interest number 1, and we actually know that x1 equals a quarter of a mile. Now we're going to plug that in. Of course, we're going to use feet. So I got 1,320 feet equals 1/2 AX, and they gave us a time. It's the other thing that they gave us, times 9.7 seconds. All right. Solve for AX. So I'm going to divide, and that's squared. Don't forget to square that. So I've got 1,320 divided by 9.7 squared times 2 to get rid of our half equals our AX. So we can calculate that. Let's just see what that is. So 2 times 1,320 divided by 9.7 is a very large number. There's double checking here. position 1/2 axt squared. Oh, sorry, I got to square my time. I didn't square my time. I got to take this 9.7 seconds and square it. So 2 times 1320 divided by 9.7 squared. This is better. And I get 28.1 feet per second squared. Now you notice how I stopped. I was at my calculator. It showed up as 272 feet per second squared, and I knew immediately that seemed like a very large number because Earth's gravitational acceleration is at 32 feet per second squared. This was 10 times greater than that, and that just seems way out of whack. So I went back through and redid my calculation, and I figured it out. It's 28.1 feet per second squared. Much better. How many G's is this? Compare this to Earth's gravitation. All right, so the number of G's, I'm going to take this and divide it by, not 9.80, because I'm using US. I'm going to divide it by 32 feet per second squared. And I've got 28.1 feet per second squared for the Bugatti. Units cancel. It's a unitless number. This is going to be a number slightly less than 1. So this is 0.87, I'll call it 0.88 Gs. So a ball dropping has 1 G, right? The ball dropping accelerates at 1 G. The Bugatti doesn't make that. In fact, the Tesla over the 0 to 60 time frame is actually quicker than the Bugatti. But to do the quarter of a mile, the Bugatti is quickly over a quarter of a mile. So it's an interesting comparison. And it's not even close to the rocket bike. The rocket bike has double this acceleration. So the rocket bike would beat this $1.8 million car. Of course, the real car to beat is my 97 Ford Taurus, which I sold for all of $75 at the junkyard last year. So let's say I'm in my old car and I'm driving along 30 miles per hour on the on-ramp, merging onto Route 3 traffic, traveling at 60 miles per hour. And I updated this number a little bit to be more realistic. It takes about to go 0 to 60. That car could do it in probably about 15 seconds, compared to the Tesla, which is 2.28 seconds. So a little bit slower than the Tesla, but a lot cheaper. And by the way, this car still ran when I gave it to the junkyard. So any of you could have bought that off me for $75 or $76, I suppose, and I would have given you this great car. So the question is, how long does it take for it to speed up from 30 up to 60? How long does it take you to do that? And how far does it travel to get up to highway speed? That's an important number because the question is, how quickly can you merge into traffic? You want to be able to merge in traffic as quickly as possible and, of course, be safe while you're doing it. So once again, I set up the problem, drew my diagram, x-axis, and I better put some units down here. I'll take off 3 points. What units are we going to use? Well, this is in miles per hour, so I'm going to use feet for my units here. My car starts out at 0 feet. Here's my table of initial conditions right here. So I've got 30 miles per hour. That's easy to convert. That's 44 feet per second. That's half of 60. And I'm going to calculate down below here the acceleration, so we'll come back to that. I don't know what the distance is, but that's what we're asked to find, right? So how far does the car travel? That's part B. My final velocity, that's the given. I know we're going from 30 up to 60, so that was a given. And I don't know the time it takes to do this, and that's part A. It asks us how long it takes to get there. What assumptions? Constant acceleration. Is it constant acceleration or not? I mean, when I'm pressing the accelerator, I think I'm in the same gear the whole time, going from 30 to 60. So chances are it's somewhat constant, or at least as an approximate, we can assume that it's going to be constant. So you could write a couple sentences explaining why using constant acceleration equations might not be a bad idea for this. At least it'll get us in the ballpark of the answer, if not the exact answer. So I'm just going to use my good old friend acceleration equals change in velocity over change in time for my 0 to 60 numbers up above, which is 4 miles per hour per second. And then you could actually work this out and you get 5.9 feet per second squared. That's a far cry from the Tesla, of course, or of course, better yet, the rocket bike. Actually, I traded in my car for a rocket bike. That's how I get to work now. And the number of G's, if you want to work this out,
Well, I've got 5.9 feet per second squared, and the Earth's is 32 feet per second squared, just for an object dropping.
And this is what? Well, 6 out of 32.
It's a fraction, a small fraction. So I got, what is it, 5.9? So this is 0.18 Gs. This is pretty sad. 0.18 Gs compared to the rocket bike at 1.75 Gs. So I don't even feel myself getting pushed up against my seat when I accelerate in this car. It's so slow. All right, so we know what the acceleration is. I've written down equations 5, 6, and 8 to see what we were going to use. In fact, what are we going to do? Actually, let's go ahead and use equation 8. In equation 8, I know my final velocity is 60 miles per hour, but we're going to use 88 feet per second. I know my initial velocity is 30 miles per hour, which is 44 feet per second. I just worked out the acceleration. All right, we can plug the acceleration right there. And I want to find, one of the things I want to find is my change in my position. So this is a good example of where I could use this equation. So my initial velocity, let's go ahead and plug in our numbers. My final velocity, what is it? We said it's 60 miles per hour, 88 feet per second squared, equals 44 feet per second squared, plus twice my acceleration, which is twice of 5.9, times my change in my position. All right, so I can just do some subtraction here. I've got 88 squared minus 44 squared divided by 2 times 5.9. By the way, I could have done this algebraically too, right? I could have just said it's Vx final squared minus Vx initial squared divided by my 2ax. This is a general solution for my, all right? That's what we call a general solution, so I can plug any similar numbers in here. And this is the specific answer for my car. And let's just see how many feet it takes me. Probably about 3 miles to get up to 60. 88 squared minus 44 squared divided by 2 times 5.9. So it looks like about 492 feet. That's quite a ways. But no accidents yet, knock on wood. And that's my solution to that problem. Of course, now you got to ask yourself, how are you going to get the time? You can go back to these two equations and work out time. I'll let you do that.